I'm now going to take a look at the fourth way that we have of deriving the Laplace transform of sine omega t and cosine omega t. And this just takes advantage of the fact that sine omega t is the unique solution to this initial value problem. Y double prime plus omega squared y equals 0, with the initial conditions that y of 0 is 0 and y prime of 0 is omega. Okay. Now, that's not a fact that you have to have memorized. It's pretty easy to come up with a second order differential equation, initial value problem, for which sine omega t is the unique solution. Okay. And once we have that, we can go ahead and take advantage of that. What I'm going to do is I'm going to take this differential equation, I'm going to take the Laplace transform of both sides. Exactly what I'd do if I were trying to solve this by taking Laplace transforms. Except I'm not going to need to take the inverse Laplace transform of what I get, because I know that that's going to be sine of omega t. I'm going to stop once I've found the Laplace transform of y, because I know that y is sine omega t. Now, we are going to be required to take the Laplace transform of a second derivative. We haven't done that before. We can do that fairly easily, though, using formula 11, because formula 11 tells me that the Laplace transform of y prime, I'm going to just write that as d by dt of y, is equal to s times the Laplace transform of y minus y of 0. So what that means is if I want to take the Laplace transform of y double prime, well, I'm just taking the Laplace transform of the derivative d by dt of y prime. So I've just got y prime in the place of y. I'm going to get this formula with y prime in the place of y. So I'm going to get s copies of the Laplace transform of y prime minus y prime at 0. And that was just using formula 11. But now I can use formula 11 again. So I can say this is going to be s copies of, by formula 11, this is just the Laplace transform of y minus y of 0, and then I'm still subtracting the y prime of 0. Oops, dropped an s there, sorry. When I use formula 11 for this, I'm getting s copies of the Laplace transform of y. This s was from when I took the Laplace transform of y double prime. So if I just distribute that s, I'm going to get s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. Okay, so this formula right here is the formula for the Laplace transform of y double prime. Now, it's possible that you're going to do this often enough that you accidentally memorize that result. If you do, great. But if you accidentally memorize it, that means you got pretty quick at deriving it. I do want to see that work. So on exams and quizzes, don't just plug in this formula. Show me how you get it by actually just applying formula 11 2 times. Okay. If you want to do what we just did and do that sort of as side work off to the side and then use it in the context of a larger problem, that's totally fine. Okay. All right, so now I'm going to take the Laplace transform of both sides of this equation. So the Laplace transform of y double prime plus omega squared y is going to equal the Laplace transform of 0. Okay. So here I can use the fact that the Laplace transform is linear. So the Laplace transform of y double prime plus omega squared times the Laplace transform of y is going to equal the Laplace transform of 0. Now, let's see what that is. According to the definition, that's just the integral from 0 to infinity of 0 times e to the negative st times dt. That's the integral of 0. That's going to be 0. The other thing I could do is I could say 0 is just 0 times any function I want, but 0 is a constant. I can pull it through. So I'm going to get 0 copies of the Laplace transform of any function I want. I'm going to get 0. Okay, so now I can plug in this formula that I got from that side work that we did initially. So I'm going to get s squared times the Laplace transform of y minus s times y of 0. Well, that was just 0 for this problem, minus y prime of 0, that was omega, plus omega squared times the Laplace transform of y, and that's equal to 0. So this piece gets killed off. So I'm going to just add over the omega here. So I get s squared times the Laplace transform of y plus omega squared times the Laplace transform of y is equal to omega. Now, this is the Laplace transform of y multiplied by s squared plus omega squared, and that equals omega. Oh my goodness, the Laplace transform of y is omega over s squared plus omega squared. But remember, our y was our solution to this, and the solution to this was sine of omega t, so right there, there's the Laplace transform of sine omega t. Kind of cool. Now, we can do something similar for cosine, because with cosine, I can find a very similar differential equation to which, or initial value problem, to which cosine omega t is the unique solution. And in fact, that's what you'll be asked to do in homework problem 5, okay? But we can also do something different. And this is what your textbook does, so I'll just show you that. I can use the fact that cosine of omega t is 1 over omega times the derivative of sine omega t. That's just basic calculus. If I take the derivative here, I'm going to get omega times cosine omega t. So if I multiply that by 1 over omega, I'm going to just get cosine of omega t. This is very exciting, because now I can say the Laplace transform of cosine omega t is the Laplace transform of 1 over omega times the derivative of sine omega t, which is going to be 1 over omega times the Laplace transform of the derivative of sine omega t. And so now I'm going to use formula 11 for taking the Laplace transform of a derivative again. So that's going to be 1 over omega times s times the Laplace transform of sine omega t minus sine of omega times 0, minus my function evaluated at 0. And of course, this is just sine of 0, which is 0. So this gives me 1 over omega times s, so let's just write that as s over omega. And we just saw that the Laplace transform of sine omega t was omega over s squared plus omega squared. Cancel those omegas, s over s squared plus omega squared. Holy cow, that's the Laplace transform for cosine of omega t. So we have lots and lots of options for how we can derive the Laplace transforms of sine omega t and cosine omega t. If we just want to know what the Laplace transform is, I think the simplest way is to just take the Laplace transform of e to the I omega t, and that gives you both of them in one shot, because then you just take the real and imaginary parts. But I think it's just so cool to see how all these different ways work together. And it's so rewarding when you do something and you're like, that's the right answer. And I know that's the right answer because I just did this same problem 3 other ways and I got that answer, and it's the answer that's given on the formula sheet. So, pretty cool stuff. We're going to actually start using it to solve some differential equations pretty soon. Go figure.